All right. I don't have too much to say, but that's David Swathard, and this is the continuation of the NetOps coding 101, and he'll give you a little more information. We do have people to help if you have any questions or missed the earlier content. Thanks.
Thank you. Awesome. Thank you. So welcome back, everybody. If you're new as well, welcome as well. So this is the continuation of a tutorial from this morning where we started out walking through some of the Python basics and also showing you the model of what we use at Facebook called FBAR. Specifically, the tutorial is focused on building your first robot and to automate the detection of common network faults and write code to do the initial troubleshooting that you might otherwise do yourself. So we are going to continue and not repeat from earlier out of respect for everybody's time. But if you are new, this is going to be based on a virtual machine that everybody grabbed earlier from USB drives. Try to ask your partner if they have one if you haven't gotten this yet. It has a virtual machine of Ubuntu Desktop and installers for VirtualBox. And we also have the same as a link from the 9:30 a.m. abstract on the bottom section to Google Drive as well. So what we're going to continue on, though, is just a quick rehash of the final section at the end last time, which is where we were building regular expressions to parse out log messages sent by network devices. And I do want to actually just give you one quick demo again of what we're building. So in our VM, we have this thing called IPython that we're interacting with. We can actually run the demo code by simply typing run and nanog demo.py. And so what we see is this, imagine this code is running on your syslog server. So this is the only real part that I'll repeat to make sure we all are familiar with what we're building. So imagine this code is running on your syslog server and it's reading in the log files in real time. It's trying to parse those log files and react to them and do troubleshooting that you otherwise would do. For example, logging into a network device that reported a link failure and try to issue related show commands to say, hey, is this link still down? Is it taking errors right now? And if it is, try to evaluate the condition by checking things like, what are the optical light levels? This could potentially send you an alarm that's much more useful than a link down. It could say instead, hey, this device, switch 1, had a link go down. That link might be kind of important. It could be your backbone peering link between data centers. And it went down because of this reason, because the fiber is causing bad signal levels and taking errors. That frees you up because it gives you a much more high signal alarm so that then you can focus on building better software and other things like that. So what we're going to come back to is the final section at the end of last time, which is where we were building a regex to parse the actual syslog messages emitted from our devices, which these devices we're using to demo with are just one of the standard vendors out there. Nothing fancy. It's a standard syslog message going to a syslog server. Imagine our machine is the syslog server that we're prototyping on. So here is one of the messages that we're looking at. From 2015, April 2nd, we had a device named switch1 that reported IF down, interface removed, interface Ethernet 5/1 is down. That's the equivalent of seeing the same message in output of show log. So if you're new to this section, I am going to skip some of this because we covered all the basics of regexes earlier, but I am going to just quickly rehash this part of it because this is where we finally got to the full regex that we're going to use to parse against this log message and turn this log message from one line of text into structured data to give us things about the log message we can interact with. So what I show here, though, is the final regex that we're building. And what I want to point out, though, is it's actually several regexes combined when we go to use it. So one tip when you start to build regexes is that you can build them as individual units and then combine them later once you know that each individual piece works. So a quick rehash, we have datestamp RE. It's matching on using this /D+ to pull out 2015. /S+ to grab the space between that, /W+ to grab April, and finally it ends with /S+ and /D+ to grab the rest of this. We use something new. Earlier, we use a capital /S+ to match on the host name, which simply says match on anything that is one or more non-space characters. And in this log message, the vendor here is using spaces to separate things of the log message, so we can trust that anything that's not a space at this place in the log message is going to be this data of switch 1, for example. And then the next section, we match on the actual error code or a category of this error message. IF down, interface remove. And this is where we, again, use the uppercase /s, but then we use our grouping symbols to our advantage here, the parentheses, and we say match exactly between percent sign and colon. And everything in between, we actually want to pull out anything that's not a space. And finally, when we get to error message, we match on .* to grab everything until the end of the line. And so when we parsed the log lines earlier this morning, we got back a list of log lines. So if you imagine reading the syslog file, we have each log line is one element in this list that we're walking through. So it's safe to say that the end of this log line, everything from here on is the message. And so when we go to combine this as a single regex, because what we want is to run a match against the entire log line as one unit. And what we want to get back is all these individual pieces. So earlier we built individual regexes to match the components. The date stamp, the device name, the error code and message, for example. Since they are strings in Python, we can use just simple string methods, for example, like the plus sign, to combine two or more strings together. And so what I'm showing here is that we're actually combining each individual regex with another one that I skipped called column delimiter, which is simply /s+. Because we're using spaces to separate the sections, we're just intermixing that here. So what we're going to get at the end here is this syslog, or this regular expression that will match the entire line at one time. But because we have all of these grouping elements around the different sections, it's going to give us each of them as individual attributes of data. So if we walk through actually doing this again, we have 4 line and log lines, the list of log lines we read. We say matched equals the result of running re.match. And if you saw this morning, we imported the module called re, and we're using the method called match. Passing in the pattern, the syslog, or the regular expression as one thing, followed by the line. If it did not match, we end the flow of logic here and go grab the next line and try again. But if it did match, we're going to expand out the results of the data that we grabbed by calling match.groups. And so matched here is an object that the regular expression module gave back. And it has a method called groups that will return us back all of the elements that matched in the order that it matched. And so what we see here is we can assign each of those attributes of data to variables directly. For example, date stamp, timestamp, device name, error code, and error message are now variables of exactly that portion of data from the log message. And so what we use just now is this call called groups off the matched object. I want to point out, because we covered this briefly this morning, in that we're using parentheses in our regular expression pattern to say where is each group. So we could build one giant regex to match all this. And that could potentially work. But by using these parentheses intermixed between it, we're saying this is an actual unit. And we don't really care about things that are not in parentheses, even though we're using them to do our logic to match on. So when we go through this, because the final regex is a string combined together, that will maintain the order of each of these individual component regexes. And so that order is maintained as well for the grouping. So when we call .groups, the first group will be the first thing in the regex that matched. Okay, so we just ended the last section on this portion, and we really didn't have time to try it out. So I want to go back to that so that everybody has a chance to interact with this. So in the virtual machine that you've got, okay, so back to the virtual machine. If you open up the terminal, it automatically goes into IPython. We have one hack in here in that we've already put in the entire regex here so that you can actually interact with it and not have to get stuck on that part. So if you print in capital syslog RE, you'll see the entire regex that was combined in its final form. And this is exactly what was passed. Hold on. There, okay. So, yeah. I just want to make sure you can see this. So what we see here is one large string that is the regex we're using to parse against this syslog message. It's a little hard to read right now, but this is everything we built going up to it. And what we see here is actually intermixed the grouping symbols. So here we see group 1, followed by things that are outside the grouping symbol. Those are things, for example, the /s+. That's the variable we called earlier called column delimiter. We don't really care that there is spaces because we just want the data after it. But we're going to use this to separate between the groups. And so when this matches, that will be thrown away. And we'll use the data in between the grouping symbols. So you can start to see this. So for example, if we look at the log line we're looking at. Okay, so here's one of the log lines, for example, that we're going to be parsing with this regex. And so log lines is a list of log lines we read earlier, and I'm just accessing the first line in this log lines list by calling bracket 0. It's just a way to directly access an element. So this is the regex that's going to match against it. So we have here matching on the date. Here's going to match on the time right here. And this, for example, will match the host name, and so on. So you have this in your IPython right now so that you don't have to go through the pain of typing all of that. Because I want you to actually try out interacting with the log lines and getting back this matched data. So if you do, for example, for a line in log lines, and try this out. Try saying matched equals the result of re.match, and you're going to pass in the first thing is the pattern, syslog re, followed by the thing to match against our line. And so this hasn't ran yet because we're in IPython, and so it's going to let us type some more code. So let's say if it did not match, continue, which allows us to grab the next line and try again. If it did, though, we know that if it did match, we know that all those groups exist. And so it's safe to access them. And so we can now print matched.groups, for example. And if we hit enter again, that will execute the logic. And what we see now is that we have, for each line that we walk through, a tuple back of each individual piece of the log message. And so that's still a tuple right now. Let's make this a little smarter, though. We can directly assign those elements to variables, and then our code can actually interact with those variables by just changing that slightly. So we know that we have 5 things that we're matching against. And we already have names in our mind of what these are. The date stamp, the timestamp, the device name. So we can directly assign those to variables right now by just doing this. So we do datestamp, comma, timestamp, comma, device, comma, and then the next part was the error code, and then finally error message. And we'll say that equals the result of calling match.groups. At this point, we can interact with the individual pieces of data from our log line. For example, device. We see now that we're looking at switch 2 and error code. And finally, error message. So this is one of the really big hurdles to getting into building something like FBAR or automating these kinds of problems, because it is a lot to get over until you get to this point, because you've got to get familiar with regexes. But the cool part is that we just built a pattern that matches every message sent by this platform and this vendor. So if you only have one vendor and maybe even only one major platform, you only have to do that part once to get the regex parsing into data. And if you even if you have a handful of vendors, once you've got the first one down, the rest you'll see are a lot easier to plug and play because you just keep trying different combinations until you get back the data that you need. Okay, cool. So, yeah. Okay, so let's put that to use. Let's try building our first remediation now. Okay, so I mentioned earlier that the VM is customized with some other modules and such. One is this thing called Paramico, which is a Python library to do direct SSH from Python code. It's not normally with Python, but it is an external download or install. Still simple to install, but we have that on the VM already. It does take some legwork. And out of respect for time, I'm not showing you that legwork, but I'm doing something different. I'm giving you what we use at Facebook to make that legwork easier. It's a file called SSH helper that you'll see in the VM on the USB key and also on the Google Drive link. It's almost word for word exactly what we use to interact with SSH. It's simply a helper that handles all the boilerplate code of exactly how to set up the connection, how to do some specific things that make it work for network devices versus servers, for example, and some ways to make it a little easier. So I'm going to be demoing with that module so you know how to use it because it's much simpler to start with that than to actually open the whole SSH logic and walk through that. So the first part here to get output from the device using SSH is that we're going to import this module called SSH helper. Okay, so if you're not in the VM and you just type that, this is probably what you saw. So I tried this on my Mac natively before I installed it. I get a traceback that says import error, no module Paramico. It's a simple fix, but it is something to be aware of. And if you missed the talk earlier, one comment about Python in specific that makes it a little different than some other languages. So it's what's called an interpreted language, meaning that any Python code runs against the local interpreter and whatever files are installed in that machine. Perl is the same way. Which means that if I have Paramico installed and I build all this code, and then I ship it to another server, and that server does not have Paramico installed, my code will no longer run. And so now I need to worry about what's called a dependency of installing Paramico. It is just a caveat to be aware of in like production environments. But if you're on something like Linux, it's slightly different on Mac. But if you're on Linux, for example, like Ubuntu for here, we have this handy helper called pip, which is part of one of the Python packages that you can install on Ubuntu, which automates locating and installing of third-party modules that are not natively with it. So if you were missing Paramico, you could simply type sudo pip install Paramico. The sudo here being that it requires root privileges because it's installing in non-user directories. And it's just a few lines, and that's relatively quick. Now, if you did not have pip, you can also install this from source, which is what I did for the VM. It's a little bit more involved, but it's not that much more. Okay, cool. Let's go back to what we're actually building, though, because at the end of the day, we want to build something to handle some of these network faults and make our lives easier by either troubleshooting it for us and potentially redirecting traffic, or at least doing enough of the work so that we know exactly what's wrong without having to dive into it. Okay, so we're back to our log line, our log message. Switch 1, interface down, interface remove. And so this is right where we left off earlier. We parsed out the individual pieces of data. And so now we have these attributes that are the result of calling match.groups. And so simply put, we can just look at the individual error codes and start building a map of them from our own experience of what these might represent. In the same way that as a network engineer, when you see certain messages, you automatically troubleshoot in a certain way, we're going to build our code to do just that as well, because it's replicating us. So we say, if IF down interface removed in error code, Well, if we look at the code we ran earlier, the demo, we're going to print, hey, I found a known error on. And then we're using something new here. We're using string substitution to interject the device name in the middle of the string using these braces with the 0. And then finally attempting remediation. And then to do that string substitution, we just use this .format call. And .format takes in one or more arguments, and it will replace the things in braces with those. The 0 here being the first thing if there were multiple. So what we go next to is that we need to actually start interacting with this device to get some more data to troubleshoot it. So this is where regular expressions come back, and that we really want to issue the equivalent of like show interface and get some stats about the device. For example, is the interface still down? Did it come back up? So here we build another simple regex to say parse out the module number of the interface. And what I mentioned earlier this morning is that we're approaching this log message as being suspect for a line card failure. So even though it says interface removed, which could be something as simple as pulling an optic out, in the case that prompted this remediation, we saw interface removed for all 48 ports on a line card at the exact same time. The line card crashed and rebooted, and there was no other message that the line card crashed. So we built the logic here saying that when we see this, let's at least troubleshoot the module, because maybe that's suspect of a software glitch versus a hardware problem. So here we're going to piece out just the module number. And it's a slightly different regex than before in that we're saying dot plus followed by slash d plus in parentheses. So the parentheses here are the thing we care about when we finally do the match. But after that, we have a forward slash followed by a backslash. I think I slightly screwed that up. But what I meant to say is we're trying to do an exact match on the forward slash because of the forward slash. This screenshot is a little new. It might be slightly wrong. But what we're trying to get here is to match out 5 from 5/1. And we're using things around the grouping symbols to get to that point because we're running this regex against the error message. So here the error message is everything from interface Ethernet 5/1 is down to the end. When we run that, we get back this thing called interface. And so when I looked at this earlier, I said if not interface or if not match continue. I'm showing you here what actually the if statement is doing under the covers. It's simply calling the equivalent of the bool function to say, does this evaluate actually as true or false? So if I print the result of calling bool with the value of interface, I see that it's true here. So if I simply printed interface, I would get back the object would print, which wouldn't really tell me much other than that the class name and the memory pointer would be shown, because those are defaults that print when the actual code doesn't define what prints. But here I simply just know at this point that this regex did match. And so now I can use the data from the match to intersperse that in new commands that I issue to the device. So what I'm trying to get to is the equivalent of running show module 5. Because I want to see if module 5 is still down or if it came back. And so when I look at the matched object I got back, I can use this group method again and pass in the number to say what group I want to get. And by saying group 1, I'm going to grab the first set of parentheses, which in this case we only have one set, which is going to match the slash d plus before the slash. Oh, I was wrong. That is going to work. So ignore what I mentioned on the slash. That should match. So we mentioned earlier the backslash indicates that a pattern matching character follows. The forward slash is not going to match anything. But there are ways where you use the forward slash to say ignore what follows. But in this case, it should match the exact forward slash, but throw it away because it's outside of the grouping characters. So that gives us the module number, and if we print the module number, we have 5. Okay, cool. So we're starting to grow here a little bit. So now we can build a command to send to the device, show module 5, and then try to run this. Okay, so that was a lot to throw at you real quick. So I want to break for another quick try it out section. I want you to create a regex to pull out the module number from what I've shown here, Ethernet 4/48. So in your IPython shell, go and create a string that's equivalent to Ethernet 4/48. And then try to build a regex that will match against this and specifically match and pull out just the number 4. Once you get that, try substituting that number into the command show module and try printing that. We're going to take a few minute break for this. We also have helpers throughout, so if you get stuck or have questions, please throw your hand up. My helpers are Brandon up front. I've also got Joe up front and TJ over here as well. Cool. So go ahead and give that a try. So if you take a look at the screen where I just tried this out as well, out of curiosity, I just wanted to try seeing if I could build a regex that was a little bit more constrained to only match the digits. So my first try, so here's where I created the message. Ethernet 4/48 is down. And what we're trying to parse out is this module number, the number 4. So you might have immediately thought of trying what I did here, of saying, well, let's just look at the set of digits broken out by the slash. In some cases, that might work, but not with the re.match method. There's another method that would, called re.findAll, but we're not working with that right now. But if we try to call re.matched, it's going to try to match this at the beginning. And so if we call this, so right now I have Ethernet in front of that. So because I don't say anything is in front of this, this is the equivalent of having like the caret there start a line. And so I called matched and I said re.matched, passing in my regex and followed by the message. When I printed it earlier, I got none. When I changed that to say match on dot plus, so anything and one or more of anything before it, then it did match. And what I did here is I printed matched again, and I get back the generic print statement for an object. That doesn't really tell you much other than that it did match because you got an object back. And so what we can do now is say print matched.group. And we could say group 1 since we know that the module number is group 1. Like we used earlier, we could actually also use groups. So group singular takes in an input of the number of the group you want to access. If we call groups plural with no input, we get back a tuple of what matched. Now, having the tuple of one element is still a little tricky, but if you had 5, like we had earlier, we get all 5 as one thing. So right now we have the module number as the result. So we could say module number equals the output of matched dot group and call 1. So if we print module number, we can now use that to build into the command that we want to run against the device. For example, if we say command equals show module, and then we put in the string substitution characters using these brace notations followed by the number of the thing we're going to substitute when there, for example, if there's multiple things to substitute, you could actually say like 1, 3, like so on, and it's just counting the number of the inputs. But since we only have 1, we're just going to say show module, brace 0, and then call dot format after that to replace the brace with the thing, which is in this case module number. And then if we print command, we have show module 4, a command that we might type on the device. Okay, cool. So let's actually go back to using that and really try out talking to a device over SSH. So to do this, we import SSH helper. And then we simply open this instance of SSH helper's class or object called SSH session. It takes only 3 inputs at minimum. It takes in a device name, a username, and a password. For the purpose of this demo, I have a small hack in there that will actually make all of this work. So it will take in any device name, any username, and any password today. It is only a 3-line hack at the bottom of the file, so when you go try this out on your own, feel free to remove those. But that's all we're using, so that you can actually try it out and build code that would still work, and that you could actually mock up and test on your own before you talk to a real device. So what we do is we import SSH helper, and then we create this new variable called SSH. It equals the result of calling SSH helper's SSH session by passing in device name, a username, and a password. I actually want you to try this out so that you're familiar with this part. So go ahead and try to import SSH helper. And then here's something different that we haven't shown earlier, in that Python has built-in help. So if you're on an airplane and you're trying to learn some code, this is actually really handy. When prototyping this demo, I was flying back to Ohio one day, and I was trying to work with some of the SQL modules, for example, and try to do the database stuff. And I'm like, I'm on an airplane for like 4 hours straight, no internet access. I didn't want to buy internet access. And so I just started fumbling around with the help. And it told me everything I needed to know to the point where I was able to build and prototype what I needed. So try this out. Try importing the module named SSH helper, and then try calling help. And then the help function takes in whatever you want help on. And so it's going to try to read into the code. And if the code has what's called doc strings defined, it's going to show you those doc strings. But which are comments that as developers we can write to help each other know what our code is supposed to do and what the inputs and outputs are. If there are none, though, by default, it's still going to give you some details about the inputs and outputs, so you can at least figure out what you need to send it to use this. So go and try that out. If you have any questions, feel free to raise your hand, and we're going to just take a quick 2-minute break through that. Yeah. Let me actually show it. So the comment was the output of help SSH helper is not very helpful. Let me actually show what that is, and let's walk through that. Okay, cool. So what I'm showing here actually is, I really wanted you to more get familiar with calling help more than anything else. So when I mentioned doc strings earlier, those are different types of comments that can exist at different places in code. And so SSH helper is actually the module here. And so what I'm showing right now is that you can actually read module level documentation, if it exists, by calling the help command. But what I actually meant this hands-on portion to be was actually for the class. So if you say SSH helper.ssh session, thank you for pointing that out, by the way. This is what I really meant for you to try. This is to see the doc string of that object or that class to see what the inputs and outputs are of it. So if you call that, and you can do this with any function. For example, when we're working with re.match, you can say help re.match and see what exactly it wants to take in and what it returns. And so here, I see class SSH session. It shows me its doc string as well, followed by what really matters is the section called init. We're not going to go too deep into objects here because it can get pretty deep on its own, and it deserves its own class. But what we see here is ignore self, which just talks about an instance of it. And the things after are the required inputs. For example, device. And it actually has a default username and password of empty string, so you could really call this with only passing device. And then what we see below here, though, is I mentioned on the matched object, we have methods called groups. Just like that, we have methods on this object too, like close and write. And so we're going to be actually using the write command in a minute, and it takes in one input of commands. Cool. So with that, let's kind of continue on. So now let's talk about how to send commands to a device over SSH. So we've got our show module command. For example, show module 5 or 4 from what we just did. And let's try writing that. So if we type in show module equals the result of SSH, which is our object from SSH helper of the session, and we call write, we pass in the input, which is actually expecting a list of commands. And since our command is one string right now, we put that string or that command into a list of one. And so if we call show module equals the output of that. Yeah, so if we look at this, the command is show module 5 that this is based on. If we call output, so output equals the result of what we ran. So that would be the same as if you ran show module 5 on the device and you were just looking at it on screen. So what I want to show here, though, is how we could kind of inspect the output. Actually, before we go to that, I want to show you that, though. So let's say our command was show module 5. And I know we did 4 earlier, but I think the actual mockup is based on expecting number 5 in this. So let's say we have show module 5 that we want to inspect. So SSH equals SSH helper.ssh session. Oh, and one tip, if you're in IPython, you can tab complete, and it will finish to the point of being unique. So we pass it a device. You can actually pass anything in this case. So we'll just say switch 1. And I don't think username and so username and password are not actually required since we're using the demo. If we call ssh.write, and we pass it that command in a list, it's going to try to run it. And since we're in IPython is going to natively print out whatever return back if it returns something. So this is the same as saying output equals the result of this command. Okay, cool. So if you're interacting with SSH, there's obviously going to be some delay. For the purpose of this demo, there's a sleep statement there. So we have this output. So we can now inspect it and start interacting with it and try to build our code to look at it. So what I show on the next slide is how to look at it, a subsection of that output. And I wanted to show you actually something a little helpful to interact with things like lists and dictionaries. The module called pprint, or prettyprint, is what it's actually called. So if you import pprint, which is included with all copies of Python, and you call pprint.pprint and pass it something, it's going to give you a nicely formatted view of what you're printing. Let's say we only wanted to print the first 5 lines, though, of this output. We can use this new term here called slicing, which is where we access specific index positions and specifically a range of positions of this list. So what we see here is we see output, and in brackets, we're accessing 0:5. That means everything after 0 up until but before 5. So this should actually grab us the first 4 lines if I did my math right. And so what we see here is if we start to think about inspecting this output in code, we could say online equals false. So have like a default false in our code as it's evaluating the device. And let's say we ran show module, we're trying to decide if the module is online right now. So for line in output, we could then say, do we see the status of OK in that output? So what I mentioned earlier is that there are fancy APIs with bunches of devices now. But if you have no API, this is where you can build regexes to parse whatever it is you want without having to wait for a code upgrade or something to be supported. And so here we can literally just parse that output and say, if OK is in here, which we see right here, then we can say, well, we see OK, the module's online, or potentially other codes. And this is where you might want to have a list of codes based on the different platforms you have and those modules and what they report. And what we're doing now is we're actually checking without using a regex, because the regexes are great, but they're not always needed if you need just a simple question to be asked. And what we're saying is, if OK exists in this larger string, the line, that's the same as using a regex without building the whole pattern. And what we're actually using here is line.lower to turn the entire line into lowercase so we don't have to deal with thinking about, is it a capital O or a lowercase o, which might change over time. And if we see that, we say it's online, which could then break apart our flow of our remediation, what it's doing. And so now we can look at online is true. Okay, so now I want to take a quick break to have you try that as well. Specifically, try creating an instance of SSH session. All you need to pass in is some value for the device at the beginning. And then try writing show module, number 5. And try to look at just the first 4 lines of output using 0:4. And we'll take a quick break for that. If you have any questions or get stuck, go ahead and raise your hand. Oh, so the question was, why did I call pprint twice? pprint.pprint. So this is a case where in the module, the function is also called pprint. So when we imported pprint, we're importing the module, but then to access anything under the module, we have to call module.thing. So for example, with the, so in this case, the namespace, which is the module pprint, has a method by the exact same name called pprint. So this is one case where you'll commonly see it renamed. So if I just import pprint, the namespace is pprint. But sometimes you'll see people import pprint as pp and say pp.pprint. And so now the namespace is shortened to just the 2 letters. That's perfectly fine. It really is more personal preference. I found it personally cleaner to just have a hard rule of always importing and stopping at the module and then accessing everything by the module, because then you don't have to deal with tons of import statements that are inconsistent over time and all that. Any other questions right now? Yeah, in the back. Cool.
Actually, I came here a bit late, but I had a simple question for you. Like, can you like highlight the difference between this library and NetMiko and Paramiko, which are?
Oh yeah. So that's actually a good example to show you what we've done. So I'll actually just show you the code real quick because this is a good point. Okay, so I'm looking at the same version of SSH Helper just on my Mac right now. So it's actually not a ton of customization. It's just a few pieces of what we call boilerplate or stuff that we would repeat in other places of code. And so what we have is we're just defining a class ourselves here, and it takes in a few inputs: device name, username, password, and then it connects on creation of the class. Now, that's not anything special, though. What is actually different here is what's under connect. So there's a few things that we found while just troubleshooting this. One thing specifically is that it tries to look at or work with the known host file on the current box. So if you have this basic setup of basically saying auto add any missing keys. That's actually not a big deal. The other point is more of these other few lines that just repeat all over our code. Finally, the section with write is a bit more involved in that we found with a specific platform that we had that if we just tried to call the equivalent, so actually let me just walk through this a little more briefly so you know if you're in Paramiko what you'd be doing. So if you're in Paramiko, you create an object by calling paramiko.ssh client. So you would import Paramiko. And then you connect or open the connection to the device by calling that object.connect. And then you pass in a device name, username, and password. Identical to what we're doing so far. And then allow agent disables public key authentication, so you use username and password. We found that actually broke some of our devices because they would support it, but it wasn't turned on in some cases. It's been a while since I looked at this, so I'm not going to talk to these other three lines for right now. But if you look at .write, we had a few different use cases that we were running into. One was the issue of breaking up the commands into slower things to send, because we might be configuring a lot of BGP policy, for example. So in our environment, when we redirect traffic around a device, say we have a large chassis and we're redirecting like a few hundred gigabits a second, we redirect by changing BGP route maps, but we do it in a staggered approach. But we might send the entire, but for safety reasons, we send the entire set of changes potentially as one. Well, actually, I'm trying to think. There's a few cases where we wanted to send it as a line at a time, but put delays in it, but not have to put the delays in the implementation of the code that runs the drain, for example, or the traffic redirection. So we could instead put it in here and say, under write, it says delay equals 2. That means between every line, it's adding a 2-second delay. And so what we could have is a default delay and things like chunking, or, for example, of both sending and reading. So this is actually a delay on write, but while we write, we're also grabbing back output from the device. And one specific case I found that literally took almost an entire afternoon of like pulling my hair out was I had a device that if I tried to receive too much data at once, it would choke and the connection would hang, and the device would actually stop responding. The device would be fine, like handling traffic, but that SSH connection would just crap out, and I wouldn't actually get the output back. So what I'm doing here is I'm actually walking through, and so if you look under this while loop, I'm asking the actual Paramiko module, are you ready to send me data? And so it has this function called receive ready. That's just a true or false. And so if it says I'm ready, we walk through and only grab right here 8 bytes of data at a time. Because the issue I ran into is one device had a problem where if it tried to send too much, it was a specific platform. Like this might not even be a problem for you. But I just wanted to show this so that you don't have to fight the same problem and have to reinvent it if this would work as a drop-in replacement. That's actually basically the majority of it is really these bugs or on our platforms that we ran into where we had to both slow down sending commands and also swap to slowing down receiving. The final reason, actually, I think that's it. Does that make sense, though? So there's not actually a lot of code in this, but for the purpose of the demo, I don't have actually anything I can SSH to. But if you look at the last 3 lines, those are the hacks that make this work for right now. We're simply looking at your host name, and it's returning a different version of it right now. Cool. Yeah. Oh, you're right. Yeah, yes, yes. I'm not good at math. Cool. Any questions before we continue, though? Okay, sweet. So we're going to go going forward. Okay, cool. So then all we've gotten right now really, though, is getting the output of show module. So we looked at it and we said, if it's online, do something. So now we're going to just kind of walk through and say, run another command. Let's go ahead and grab the uptime of that module to try to figure out if it's rebooting and power cycling or if it was just a one-time glitch. Because we've seen cases where a module will reboot, but it'll be fine for days or months and just be the result of a software issue. So here we can go check the output of show module uptime. But in this case, this platform does not, so it has show module, and I can pass like show module 5, for example, but this platform wasn't quite consistent, and so uptime is all modules or nothing. So here, I wanted to show that you can do your parsing on box as well if the boxes will let you. So this platform actually has grep and egrep on the actual network device. And so I can parse the output of show module on box to egrep to grab really the section I care about so that I can make my inspecting of the output a little bit simpler. Now, one thing you might be thinking about, this really only works, this kind of like depth of using specific commands on box, really only makes sense if you have a common like standard of what devices use and maybe a small set of variation. So your mileage may vary with that part. For us, we've been lucky in that we've stayed with generally a few platforms and a few models and try to run them until they're no longer available, or until we get something better that works better. But it's not, we generally don't try something out for 5 months, try the next product. We generally keep to one product for a while. So here we get that back the output. And so now what we could do is actually get a little bit more tricky and parse the uptime and then react based on the value. This is where if we had a database, we could start storing the fact that we saw this and start saying, well, did this happen yesterday? Because I showed that the module was up for 45 days. Well, that's based on my code running 45 days later. That would be helpful if we could keep track of that and keep running it each day, and then think about how long it's been up. For the purpose of time, I don't show that right now, but I just want to throw that idea out there. Okay, cool. So that was the simple remediation. Let's take a look now at a little bit deeper one of a link that went down that we suspect might be flapping. So imagine your 100 gig backbone link flapping every 5 or 10 seconds. Things might reconverge, might start passing traffic. If you lose a second of traffic over that at full utilization, that's a lot of traffic. And that's a lot of unhappy people. So we want to detect that. So here's the second log message we have. IF down, link failure, interface Ethernet 1/4 is down. It's slightly different. Link failure instead of interface removed is really the big difference here. So we get back the same exact regex before, we get back the exact same data from calling match.groups. And now we're simply looking for the presence of a different error code. So if you're looking at the code, a simple implementation of this is simply a big if, elif, else block. So an if, else block of, is it this code? Do this. If it's not, is it this code? Do this. We'll show you a little bit later towards the end of how to clean that up and make it scalable. But for right now, we're just checking if this other code exists in the error code. For the purpose of time, I'm actually going to pass this because we just did the equivalent of this regex. But let's go and continue right now. So we've got back interface equals re.match, the output of /d+, and we're actually doing a slightly different match this time. So now we have the grouping symbols around the entire thing instead of just the first number. But that's really the only difference. And so what we get back is if this matches, we'll have group number 1 be these parentheses symbols around /d plus, the / and this other /d plus. In other words, we'll get back 1/4. So we can intersperse that again in the command that we send to the device. Show interface Ethernet 1/4. And as we did before, we just send this using the SSH helper, write commands, and we get back this output. And then if we walk through 4 line in output, we can now start to look at this. Let's say we're considering that this interface going down. Let's say that we really want to check to see if it's flapping. So now we can look at interface resets. Specifically building a regex to match on the output of show interface and to look at the value right before the text of interface resets, which is what we're doing here. So what we're matching on is with the caret beginning of line, followed by 1 or more spaces, and then in parentheses saying we care about the next thing, which is 1 or more digits, followed by exactly a space and the words interface resets. And we're looking at now in the output of line.lower, lowercase in the output that the device gave us back. Just a simple way to make sure we don't have to think about that. And we say if not interface resets continue, so that way we could grab the next line and try again. But if we did, we now know that interface resets matched. But what we matched on and what the data is that we get back when calling that group command, that data is going to be a string, which means that we can't do math on that. We can't evaluate it to say how many times has it gone down, for example. So we pass that to this function called int to convert it from a string to an integer in Python. And so what we say here is the number of interface resets equals the equivalent of the result of int interface resets dot group 1, which should be, which would be the number of interface resets. And then we can evaluate that and say if the number is over 10, let's say it's just an arbitrary number for right now, let's do something different based on that value. So if it was one link down, we may just send an alarm that, and if it's still down, just send an alarm to say, go check this link is down. But if it's going up and down, that's actually more of a problem for us based on the traffic volumes. And so we want to do a little bit more. So here we just say a print message. The interface resets are too high. But then we can go check a little bit more, ask the device again. What are the interface light levels right now? The output of show interface Ethernet, for example, 1/4 transceiver or transceiver details. And then we can use onbox egrep to parse out so that we can filter that output a little bit to only look at the receive power or the line where receive power is listed. So this is kind of a way where you start to get into something that would be really cool to have code doing for you. Because by having the code go ask what the light levels are, you could start reporting on links that have light levels. Imagine getting a report in the morning that says, hey, these 10 interfaces have bad light. They're going to be problematic in the future. They should be checked or they should be cleaned. Instead of having to get the call at 2 a.m. when they're bad enough that they're taking down your site. So now we're just asking the device using ssh.write, what are the light levels? And so we say, 4 line in output. So the output is the data we got back of, think of this as show interface transceiver. And we say the light level power is the equivalent to a new regex to match on, based on the output of that data, the number that we see in the power levels. So for example, we're looking here for the word power with anything before it, and then after power are 1 or more spaces. Now we see the grouping symbols again, and this is what we're actually trying to parse out and what we care about. And specifically, we're looking on exactly the hyphen, because it's a negative power level, and then 1 or more digits, a dot, 1 or more digits, and then the end of the parentheses, followed by a space and dBm, the notation for power levels. And then we just pass to that the output of line.lower, so the lowercase version of what the device gave us. And so if we get that back, the result is still a string, so we can't actually act on it yet. But instead of being an integer, it's actually what we would want to call a float, because it's got a decimal point. So now we've done what we're calling casting a string to a float. Simply put, we're converting from one type of data to another. Now, you can't do this for everything, but things that can be converted, you can. So if the string is literally quotes 1, and you call that, and you pass that into the int function, you will no longer have a quoted version of 1, you'll have 1. Which lets you then do math about it. So you could, or print it directly. So for example, if I print this, the output in this case was negative 8.84 dBm. That allows us to react in code to what the current light level is. And this is a good example where your threshold might be more conservative or more aggressive than what the vendor alarms on. I think this vendor actually alarms on like 13 or 14. But in our case, on this platform, we wanted to alarm on 7 to give us room to check and clean it before it becomes an actual problem. And so here we say if the power level is less than negative 7, let's go run some other code. And for example, an alarm saying, warning, the power level is too low. At Facebook, this actually goes another step further, and we redirect traffic off the interface in what we call draining by changing BGP policy for the sessions on each side. And so we remove the link from the flow of traffic and then send an alarm or an email specifically to the group or in the data centers that actually handle cleaning the fiber. So it's no longer a massive issue for us because we've detected it before it has gotten bad enough to cause actual errors. But we've also taken traffic off, so that way now we eliminate the human ping pong back and forth when somebody in the data center wants to actually work on it. Because in the past they would have to go say, hey, I got this interface, I want to go clean it, can you check is the traffic okay? Somebody on NetOps or one of the network teams would have to say, yes, traffic's okay, we can shift traffic off. They would then log into the devices, change BGP policy to get traffic off of it. And that might be a half-hour experience before the person in the data center can even try to clean the fiber. Now we've got tooling to handle all the draining stuff that we just signal say, hey, we need to drain this link. It's smart enough to know whether or not it's safe, because it potentially will block FBAR in this case. But if it is safe, then it'll let the flow continue, and then we just fix them as we have time in the data center. Okay. Are there any questions so far? Because we're going to break into kind of the next evolution of this, of how to scale this bigger. Yeah. Yes, I actually just thought. So a dot is actually, good point. So there's actually a mistake in this regular expression. So a dot in this one is going to match any character. What you actually want is an exact match for a dot. So here's how you change that. So let's say we had Rx power. And so what I originally put was dot power. So the dot here is one or more of any character, or dot plus power, followed by slash S plus, and then in the grouping symbols were the actual match for the value we saw from show interface transceiver, the negative, slash D plus for the first digit. Here's the mistake that, thank you, I forgot your name. What was your name? Matthew, cool. Matthew just pointed out. So I actually put just a dot. So that technically does match, but it won't match exactly a dot. It'll match one of any character. So what I really want is to escape the match of that and match exactly the dot by putting a forward slash instead of any other slash and instead of the dot itself. So if I put a forward slash, that means ignore what's next and treat it as an exact match, and don't treat it as a regular expression. But that's only for the exact character after this. Backward slash. Wait, that one? Okay, my bad. Okay, sweet. I've looked at these slides so much that it's awesome. Cool. And so what we say is backward slash. Ignore what I just said. Backward slash. What was your name? Thank you, Casey. Awesome. So backward slash dot. And then we do, again, the backslash D plus. And then we close our parentheses to say this is the end of the group. And then I had an exact match for an S, but we could also use slash S plus here, followed by the exact match of dBm. And that was in the output of line.lower. Now this is going to break, oh no. So my line right now is the last thing I worked on, so it's not actually what the slide's looking at. But that technically should match the output of that. Actually, let's try that real quick. Okay, cool. So if you're not familiar with this output I'm showing you right now, I actually have a sample of it in here. And so if you look at a common device, it's going to give you actually a bunch of data. And the reason I pass this to egrep on box is the actual output of the device is in a pretty formatted table using things like hyphens, and it's meant to be human friendly because it actually gives you a ton of data. Things like what are the optical power levels of both receive and transmit, and it also tells you what are the alarming levels of that platform. So I cut off in this output by using egrep to only grab the line that contains either capital Rx or lowercase rx, because I didn't have a way to tell the device grab by lowercase version of this output because it didn't understand that. But with egrep or grep specifically, I can pass multiple things, and if either of them match, it'll give me the output. So here I was actually looking on this value, which is actually the line. Yeah, so if I look at this, in this case, output and then the element number 1, or at position 1, the output that was actually, that we care about was this line here, Rx power. And then the first value, I just know by looking at that platform that that is the current value of it. But then the other numbers are different thresholds for alarms. I forget what this one is, but this negative 13.397 is the actual level where that device sends an alarm or a syslog message. Well, in our case, we generally see that by the time it hits like 10 to 11, it's causing enough problem that users see the issue. And they're either having a bad experience on Facebook or it's causing a bad experience internally. So we generally have a limit of about 7 to 8 is where we try to get traffic off of it and try to fix it. Generally by cleaning the fibers or replacing the optics or replacing even the patch panel ports. And so what we're using this, we're trying to match here is the regex we just built is specifically to pull out this first number here, 8.84. Are there any questions so far? I know this is like lots and lots of regexes. I hope this is useful so far, but do we have any questions before we continue? Okay, cool. So the next major section I want to go in through is more of like, how do you make this real world ready? So hopefully in your mind, as you go through this, you should have a lot of questions, because this idea is what really runs our network at Facebook. It allows us to have a single person being on call by replacing most of what we used to do by code, which means that most of us now just write code to do that. But there are design issues as you try to build this bigger, and I just want to share with you some food for thought and things as you're trying to start this on your own to make you, just to be in the back of your head. So the first major problem, and if you're actually looking at the code, all the code I'm demoing with is on like the directories and the USB key. There's actually 2 copies. I've been demoing with one called NANOG demo.py. I put together a sample of like an improved version called NANOG demo better. That gives you something to look at as an idea to apply what we're going to look at. So if you run that one, it changes slightly. But the code, if you actually look at it, will be a lot easier to follow and read. And it's doing the exact same thing, though. But I just wanted to point that out because we're about to break and all that. That you have 2 copies of this. One that's the really simple version that walks through kind of in the same way we did the tutorials, and then a little bit more advanced version. So if we walk through the actual problems, though, one big problem we have right now is it's really untestable. If you actually look at the code for nanog demo.py, everything is in what we call global namespace. So we walk through, this is the actual file I demoed with. Can everybody see that? Yeah, okay. And so what we have is we have all the regular expressions defined in what we call global space. So they're not under a function or anything like that. We also open the file in global space. So when things are not in functions and they're just all the way on the side here, this is what we call a simple script in Python. And so what happens here is when this code runs, everything in order top down is going to run like it is. This will lead to a really long file over time, but the hardest part is it leads to a file that can't be tested. So software testing is this idea that you eventually get to a point where you have so much code that you can't just react to when it breaks. And you can't just write code and hope it doesn't break. You have to have some way to validate that, yes, this change is not going to break these other 300 lines of code. And so the way we do that is we build test cases around individual sections of functionality. But to do that, we have to have a way for those test cases to run only exact functions of this script without running the whole thing. So that's one big problem we have right now. And so if you look through this, this is the actual code. And we walk through, and it's one giant if statement. It's actually walking through in a for statement with an if statement. So we literally walk one line at a time, try to do the match, and then we try to inspect what's in there and try to see if we have known conditions. And then right away, we try to remediate against them. This will lead to a really long file if you keep it all in one file, because imagine all these regular expressions, all these commands you're going to run against devices. It's going to become a lot of scrolling, which will become really problematic when you have multiple people working on the same file, and also hard to kind of evolve. Okay, so that's one problem, and we're going to go in a minute on how to fix these. The other design issue is that it's really confusing. If you look at what I just showed you, we're actually mixing what we could call the system code with the actual remediation code. So imagine this system that you're building as like a platform, and then you have people implementing, for example, your NOC engineers or your network team implementing the remediations of what to do. It's a nice way to split it out as you grow to have more people. But right now, all of it runs together, which means we don't have any kind of clear line to separate. The other issue that hopefully sparks in your mind is that this only runs on startup. So if I'm running this on a syslog server, and let's say I have 500 devices writing syslog messages, I'm going to have to keep running this over and over. But so far, I haven't saved any state about what's happened, so I'm just going to keep reprocessing those over and over. So we would need to make this real time to be able to keep track of what it's already worked on, but also be able to read the log messages as they come in. Because if you have 5,000 or 10,000 devices sending log messages, you don't really want to stop everything, run the script again, and start over, because you might be trying to remediate or work on hundreds of devices at once if you have a lot of links going up and down. And I only showed links, for example, but imagine any problem you might be faced. You could troubleshoot. Like a really common example that has saved us a lot of time is we've run into cases where the equivalent of show IP route doesn't actually match what the device is really doing. And so if you have a big chassis with like distributed line cards, there's ways to ask the line cards, what do you think the routing table looks like in the hardware forwarding table? And so we've had enough outages caused by those being mismatched that we literally just have remediations and alarms running in the background that are based on. For one example of this system is that there's an audit that runs periodically that says every 30 minutes, ask every device, what's your routing table? And then ask every line card, what's your routing table? And if there's a mismatch, fire an alarm to FBAR to work on it. That's an example where you can go from just simple leak downs to troubleshooting things that might just be black holing your traffic that could easily take half an hour of troubleshooting time to figure out. Okay, so we're not real time right now, and we're only reading the log message on startup. So we could fix that by kind of keeping track of messages we've read, and then continuously opening the log file and reading and looking at only the change messages. If we wanted to get really tricky, we could go into like a circular pattern where we continuously read, but then throw away after a certain age. Because one thing you want to avoid is a memory leak on a long-running thing like this. So you could, in the simplest sense, implement this as like a cron job and just run it and keep track of what you've worked on. The other sense to keep this real time is you could run it in like a circular pattern where it continuously reads, and then throws away the old messages so that you don't store them forever in memory. Okay, so the other issue is we have no sense of new versus known, meaning that if our code crashes and starts again, we potentially rerun everything we've worked on. So if you have a couple hundred events that you worked on today and your code crashes and starts again, you don't want to ignore this issue while you're reprocessing the first 100. So that's where getting into databases and interacting with data storage will let you have a way to both save the fact that you worked on something, but then come back to it to evaluate it later. Finally, I briefly just got into this a minute ago, but this is going to be really slow in the way it is right now because we're processing things in a linear fashion, in that we're going to read each message and then try to work on it. And it's all in order. So if we have 500 messages, we're going to be a lot slower than if we had 10 or 2 messages. Okay, so here's some ideas on how we can improve this. So for the first part, being untestable. We can move almost all of this out of global scope by defining functions. And instead of having all this code in global space, we can have something like this. So it's a slightly different version of the same exact thing. I left the regular expressions in global space because they're likely not to change. But then we've turned read logs into a function, for example. And so now when we want to read the logs, we just call the function. And then when we want to parse the logs, we have a separate function that takes in the log lines and runs the regex match against them. So, and then finally, the remediations are now run as a function individually. So this lets us build logic to test the individual components of what we're building here. And then make sure that if we change something, that one piece still works. But it also means that if we change a bunch of things, or if we only change one piece, we likely only have to test that one piece, depending on the scope of what we're doing. Okay, so let's look at a few of the other issues. Okay, cool. So the other part is that it's kind of confusing right now. We're really mixing what we call internal code with remediation code. So the remediation code is the things you're asking the device, interacting with it. This is actually kind of cool because it could be easily separated, and we could go from having one file to multiple files. So earlier we imported different modules. We imported the RE module. We imported SSH helper. You could easily split your code into multiple modules too. And so that's what I did with the second one. If you look at it, I actually put all the remediation code in a separate file called remediations. So if we look at the one called NANOG Better Demo, we actually have an import statement here of remediations. And so that's a file in the current directory. And then if we look at where we use that, so if we look at where we use that, we actually reference, the remediations and specifically, we actually reference them in this dictionary here. And so this is actually how I'm splitting this up and making a demarc between the code that runs the actual system or the parsing thing with the actual remediation code. And so if we look at the remediation file, we see now that each remediation is a function, which, going back to testing, means we can now test the remediations as individual units and alert when individual remediations fail, because you know what output you built this against. So if you save a copy of that output and build a test based on, I run this command, I expect this command, if that fails, you know there's a bug somewhere. But now, more simply though, we've broken this up so that each of our things or remediations is a function. So that allows you to actually separate the work too, because now you can approach each problem instead of editing this big for statement. You can say, let's add another function to do this problem. And it allows you to have a very small section of code. Like, for example, this line card one. It's no more than 40 or 50 lines. And one step to make this, as this grows, you could actually go from one remediation file to a file per remediation and grow it horizontally instead of vertically if you prefer. Okay, I want to actually point out one more thing, but I have slides to that. So I showed briefly. Okay, so I just wanted to kind of point out a section of slides on what I just showed you. So I mentioned the remediations were actually in a dictionary. This is one way to kind of simplify your code. I have a dictionary here called Error Codes to Remediations, where my keys are now those error codes that we were looking at earlier. IF down interface removed, for example. IF down link failure. So this allows you to actually pull all that out of your for or if statements and build a single mapping of, when I see this code, I run this function. And so what I have here is I imported the module called remediations. And then I made the value actually be a reference to the function itself without running the function. And so I just want to make sure that that was clear, because it's kind of an interesting topic when you first see it. So you can run functions by using those parentheses and put inputs into them and try to get data back. But you can also interact with them as if they're variables, just like this, where I say that the value of this key is actually pointing to the function. It's not going to run the function, but it lets me have a way to say, when I see this code, what function is assigned to that code without an if statement or a large for loop. And so to put that to use, we can now replace our logic of asking if this code exists in this error code by just saying for known error code, or for example, the keys of our mapping here of error codes to remediations, if that is in the error code we're looking at of the current log line, I can actually get back the function without knowing what its name is by accessing the value of that dictionary. And so here I say the remediation equals, so remediation now is a variable that is the function, equals the value assigned to known error code in the dictionary of error codes and remediations. So I really want to point this out because it's kind of cool in that it lets you completely eliminate a bunch of code to a simple mapping. So now if you think about building this bigger with a couple hundred remediations, you go to having, let's say, a file of remediations or a couple files of remediations, and then think of it as having another file that's your mapping file. And so this mapping.py, for example, could be entirely a file or a module that just has one dictionary, and it has all the import statements of your other modules where your actual remediations exist. And so now you maintain in a single place these known conditions and what functions you want to run against them. That means that when people add to that, it's a much more straightforward way to grow. But it also means that you don't have to go look in the code that actually executes the remediation of what to do. And so what we're doing here is we grab back a copy of the function on the first section by accessing the value assigned to the key of known error code. And then we simply run the function by using the parentheses as if we did before. So like when you called re.match or time.sleep, you could do the same here with those. The function doesn't actually run until you pass in the parentheses. And so here we know the one caveat here is if you're going to do this, all the functions have to have the exact same inputs and outputs. So they have to be consistent. Because you're going to basically run the function without knowing its name and pass it an expected number of inputs. And so here we pass in, say, an ID number for the event. That might be like a database number. The device name and maybe the error message to parse. And maybe the rest of the data about this is in a database that it goes and fetches from. Okay. I actually want to save a little bit of time for questions, but I do want to introduce one note real quick. There is actually some sample code of interacting with the database on the demo, specifically using SQLite, which is a way to create a database with just a file, so you don't actually need a full-on database server. There's demo code in there. It's db.py. It actually walks through creating what we call events, where we actually create database entries of the data we're parsing. And there's actually functions there to show you how to get back data from it and to update data there. It follows the same kind of language as like SQL. And if you look at the second example, that actually puts it to use so you have something practical to work from. Oh, and then the final thing, I promise, I know it's a long tutorial. The final thing is, how do we go from being linear of scale, the time? Because right now, if we have 5,000 devices, this will not scale. Because we're basically reading the log lines and then trying to work on all of them at once. That's where threading comes in, and so, which is just simply a way to parallelize your work. And so I gave you an idea here of what you could do. So right now, we're running everything under like one thread or one process. What we could do is split this up into two things. One that is our log processor or log parser that just reads the log files and continuously parses them. And then it could, for example, create database entries of what needs to be worked on. And then we could have a second thread that actually runs our remediations and does the work. Now with this, you could run them both in parallel. That's one way to scale. Another way is you could kind of take an approach to like what we're doing, in that we separated the entire log processing pipeline as its own system independent. And then that's its own distributed system scaled out as well with like a bunch of servers. But that's one way where you could say, instead of having all the code in one, you could break it out and have the syslog system separate, and then this could be then the remediation system that interacts with what to do. Okay, cool. One final note, we did throw up a Facebook group to kind of have a way to keep in touch and ask your questions. So if you go to fb.com/groups/netengcode, it's a public group. Feel free to join the discussion there and ask any questions, and we'll follow up and give you any detail we can about this or even about FBAR or problems that we face. But thank you, and I'll open up the floor to questions.